Okay, so sorry about that, my video cut off for some reason, so it's almost finished the solution to question 27. So I got to the distance that it has to travel between 0.25 and ending up is 0.23. 0.23 meters from 0.25 will leave you with a final distance of 0.48, which is what I had made the assumption of, so D is the correct answer. Okay, let's go to 28. Okay, so in an amusement park, a swimmer uses a water slide to enter the main pool. If the swimmer starts at rest, slides without friction, ascends through a vertical height of 2.31 meters, what is her speed at the bottom of the slide? So this is sort of a gravitational potential energy or energy conservation question. It also works out similar to a free fall scenario. So, but let's try to draw maybe a quick sketch here. So this is the slide. Doesn't matter what shape it is. There's the person up here, and they fall a distance of 2.31 meters. So I'll pick a system of person Earth plus Earth. It's frictionless, so there's no work done on that system. There's no work done by the slide. The slide force would always be perpendicular to the person's displacement. So the change in energy of this particular system is 0. So delta of this system is 0, and it's equal to delta U gravity plus delta K of the person, assuming the Earth doesn't move, which it's a good assumption. So the delta U gravity will equal negative delta K, and we have this as mg delta y equals negative 1/2 m vf squared minus vi squared, but we're told the person, the swimmer starts from rest, so we don't really have to worry about that vi. So we're looking at this scenario, then I'm trying to solve for speed at the bottom, solving for vf. So the vf would be equal to the square root, I guess the m's will cancel. And you're not given the mass to the person, it's not required. Will be 2 times g delta y divided by that's just it. Just 2g delta y, and sort of a negative. But what's important here is that the delta y is negative. You can't take the square root of a negative sign, so you have to incorporate sort of negative 2 times our 9.8, and the person is moving downwards, so we'll take that to be negative 2.31. That'll give us a positive number underneath the square root sign, and we'll end up with the square root of 2 times 9.8 times 2.31 is 6.73 meters per second. Okay. And that is choice E. Okay, so sort of, it is energy, but you end up sort of the person is somewhat in free fall. The only force that's really acting on, it's not the only force, but the only force that's causing the person to accelerate. So you can think of it as the weight force. So you can almost see that the equation boils down to, if you do the energy expressions, you'd have vfy squared equals vay squared minus 2g delta y, and the person starts out from rest, so vf is the square root of negative 2g delta y, which is the same expression we have here. Just making sure you account for that delta y. Okay, hopefully that's okay for question 28. Question 29, a car is accelerated by a constant force F. The distance required to accelerate the car from rest to speed v is delta x. The distance required to accelerate the car from speed v to 2v is equal to, and this is very, very similar to one of the clicker questions from the chapter 10, maybe lecture 17 or 18 this quarter. And so let's see, the distance required to accelerate the car from rest to speed v is delta x. So we know in this scenario we're looking at work equals delta k. and we know that F sometimes delta X is equal to 1/2 m Vf squared minus 0 squared. That's sort of Vf minus its initial speed. So the F delta X is equal to 1/2 m Vf squared. But to accelerate the car from, if we're doing sort of, to accelerate the car from V to 2V, we can think of a delta K from V to 2V is 1/2 m 2V all to be squared minus V squared is 1/2 of m times 4V squared minus V squared, which is 1/2 m 3V squared, which is 3 times 1/2 mv squareds. So it's actually 3 times, it has 3 times the change in kinetic energy. To go from V to 2V, it's equivalent as 3 times the energy that it takes to go from rest to V. So with the same force, you would need 3 times the distance. So 3 delta x's in order to get, so F delta x is equivalent to 1/2 mv squared, so 3 F delta x's, or F times 3 delta x would be equivalent to sort of the 3 1/2 mv squareds that we've determined from the change in the kinetic energy. Okay, so that's 29. And then 30, 31 are together. And one last question, 32. So we have, so this is sort of the conceptual tutorial-like problems. Spring and a block, I guess, are hung from a ceiling as shown. The block is initially held at position T, and the spring is neither stretched nor compressed. The block is released at time T5. It reaches a maximum speed at point U at time T6, and it turns around at point V at time T7. For each of the following stages of the block's motion, state whether the absolute value, I guess I'm missing some grammar here, the absolute value of the work on the block by the spring is greater than, less than, or equal to the absolute value of the work on the block by the earth. Okay, so we're comparing the work on the block by the spring and the work on the block by the earth. Okay, cool. Over the interval from T5 to T7, as the block moves from T to B, so as the block moves downward, once the block moves past point D, there's a force on the block by the spring that's pointing upwards, and there's always a weight force on the block by the earth downwards. From T to V, the displacement is downwards. So the work done by the spring, maybe by spring, is going to be negative because the force is upwards and the displacement is down. And the work done by the earth is positive, but the speed of the block at T is 0, the speed of the block at V is 0, so the change in kinetic energy of the block is 0. So there's no really work done on the block, so the work net external on the block is 0. And the only two works on the block are the work done by the spring and the work done by the earth. One's positive, one's negative. So work by spring plus work by earth have to be equal to 0, so their absolute values must be equal to each other. One's positive, one's negative. So equal to is the correct answer. Okay, and then from the interval from T6 to T7, as the blocks moves from U to V, so same type of reasoning applies here. Spring is still doing negative work, the earth is still doing positive work, but 6 it's moving at its maximum speed. So it reaches its maximum speed at T6, so as it goes from T6 to T7, the block slows down. So that means that delta K is negative, which means that the work net on the block has to be negative. The spring is the force that's doing negative work, and the earth is doing positive work, but we have to have more negative work done than positive work. So the absolute value of the work done by the spring must be greater than that done by the earth in this example. in order to slow it down. The spring force will have to be larger than the weight force, and they're applied over the same distance. And the spring force is varying really in magnitude, but its average would have to be bigger in order for the block to accelerate upwards from U to V, because it's moving down, but it's accelerating up, it's slowing down. So we have to have more negative work done, and the only thing that's doing negative work is the spring, so it has to be larger. Larger amount of absolute in its magnitude or absolute value than the work done by the Earth. Okay, there's one more question. So Patrick, 75 kilograms, and Dan, 80 kilograms, are at a carnival and have signed up for the bumper car rally. The bumper cars have a mass of 150. Patrick drives his bumper car at a speed of 4.2 directly toward Dan's bumper car, which is arrests. Assume the collision is elastic. Find the speed of Patrick's car after collision. So this is an elastic collision, sort of the last piece of the course. So draw a quick picture here. So we have, let's see, Patrick drives. So Patrick is the one driving the bumper car at 4.2 meters per second towards a stationary bumper car. Dan, so this is Dan, and this initial speed is 0, and the Patrick is slightly lighter than Dan, so the overall mass of this one is 225 kilograms, where the total mass of this one's 230. So it's almost equal mass. Where in that particular case, Patrick's car, if they were equal mass, Patrick's car would come to rest after the collision, and Dan would move away at 4.2, but they're slightly different. So there's going to be a small recoil of Patrick's bumper car, and so I expect probably A or E is probably the correct answer, since I expect the speeds to be Patrick's rebound speed to be almost 0. So there's going to be some sort of slight rebound because it's slightly lighter, and Dan's car will move to the right with a speed almost the same as Dan's initial. So this is probably the 4. I'm guessing it's a distractor, but let's work on that. So what we're trying to do is basically solve for V1 final in the elastic collision equations, the final speed of the incoming car to glider. So V1F is equal to the difference of the masses over the sum of the masses times the initial speed. And because the numerator in this example is only 5 kilograms over the sum, we'd expect a very small number, and it'll be minus. So it'll be 5 over the sum of the two, which would be 455, times the speed of the incoming, which was 4.2, is 0.046. Negative 0.046, but since I'm asking for the speed, I'll just take the absolute value of that. So that gives us choice A is the correct answer. And since just to finish it up, the speed of Dan's car is 2 times the mass of the incoming over the sum of the masses times the incoming glider or cart, V1 initial. So 2 times the total, 225, divided by 455. So almost 0.99 of the initial, which is 4.15. So actually, I don't know if I have that. Don't have that as an extractor, but okay. 4.15 or 4.2. Okay, so yeah, it's all because again, speed is almost, again, because they're almost equal masses, there's a very, very small rebound speed of 0.046, so into the 100ths of a meter per second, and then Dan is moving away at 4.15. Okay. So yeah, choice A as the correct answer. Okay, so it wraps up. Should wrap up all the questions for this practice exam.